given in statement 1, two inequalities, 3x plus 8 is smaller than 17 and 2x plus 8 is greater than or equals to 12. So let us solve the inequalities. So here subtracting 8 on both the sides. So we get 3x is smaller than 17 minus 8. That is 3x is smaller than 17 minus 8 is 9. And dividing with the 3 on both the sides as the positive number 3 dividing. So inequality will not change. So we can get x less than 3. And another equation 2x, again subtracting 8 on both the sides. So 2x is greater than or equals to 12 minus 8. That is 2x is greater than or equals to 4. Now dividing with 2 on both the sides, a positive number, inequality will not change. So x is greater than or equals to 2. So therefore we can say respectively the equation inequalities have x is smaller than 3 and x greater than or equals to 2. So we can say that the statement 1 is true. And coming to the statement 2, so here the common set of solutions of linear inequality, the same inequalities are given. 3x plus 8 is less than 17 and 2x plus 8 is greater than or equals to 12. So we got the solutions, x is smaller than 3 and x is greater than or equals to 2. So we can see that x is smaller than 3 and x is greater than or equals to 2. So here 2 is included, 3 is excluded. So the common solution we can write. Common solution for both the inequalities is 2, 3. 3 is excluded and 2 is included. So but it is given in the statement 2, open interval 2, 3. So therefore we can say that the statement 2 is false. So we can go with an option. Statement 1 is true and statement 2 is false. First option. We need to find the number of 4-digit even number that can be formed using the digits. So given digits 0, 1, 2 and 3. So since we need the even number, so the last digit must be either 0 or 2. So let us consider the case 1 ends with 0. A 4-digit number ends with 0. So remaining 3 places we can use any of the 3 numbers 1, 2 or 3. So we can say that we can arrange in 3 factorial ways. That is 3 into 2 into 1 which is equal to 6. That is first place can be occupied by 3, any of the 3, either 1 or 2 or 3, and the second one 1 is fixed means because it is without repetition. If suppose 1 is number fixed here, so we have 2 options, so 2 here and the left only one option, so 3 into 2 into 1 which is 6. And let us consider second case. Ends with 2. If consider 2 is the last place, then we have the 3 numbers 0, 1 or 3. And we know that in first place it cannot be placed 0 because it is a 4-digit number we required. So we can say 0 cannot be placed here. So the number of possibilities in fixing the first place is either 1 or 3. So 2 places are the possible here. And in the second place, now we can fix any of the remaining. So if either 1 or 3 is fixed here, so remaining 2 are there. So 2 in the second place and remaining with only 1. So 2 into 2 into 1, which is 4. So therefore we can say that the number of 4-digit numbers required number of 4-digit numbers, 4-digit even numbers can be given as either 6 or 4, that is 6 plus 4, which is equal to 10. So 10 is the answer, option 2. Number of diagonals of a polygon with n sides is given by n into n minus 3 divided by 2. So here for octagon, number of sides n is equal to 8. So we can use the formula 8 into, so number of diagonals 8 into 8 minus 3 divided by 2. So which is equal to 8 into 5 upon 2, that is 40 upon 2, which is equal to 20. So we can say that there are 20 diagonals of octagon, which is our option B. With the expansion of x plus y whole power n, the number of terms is equal to n plus 1. So here in this given problem, in the expansion of 2x plus 3 whole to the power 3n, the number of terms can be taken as 3n plus 1, and which is given as 22. So 3n plus 1 is equal to 22. So 3n is equal to 21. So n is equal to 21 upon 3, which is equal to 7. Therefore, we can say that the value of n can be taken as 7, which is our option 3. Let us consider first term is a and r is the common ratio in geometric progression. Then we have nth term an is equal to a into r to the power n minus 1. So here fourth term is given x, that is x is equal to a4, which is equal to a into r to the power of 4 minus 1, that is 3. And 10th term is given y a10, which is a into r to the power 10 minus 1 9, and 16th term is given as z, so a into r to the power 16 minus 1, that is 15. So here if you consider x into z, that is a into r to the power 3 into a into r to the power 15, which is equal to a square into r to the power of 18. We can write this as a into r power 9 whole square. A into r power 9 is y, so we can write y square. Therefore we got y square is equal to x into z. So y is equal to under root of x into z. So we can go with an option 2. Given A is a square matrix such that A square is equal to A. That is A square minus A is equal to 0, or A minus A square is equal to 0. And here I is an identity matrix. I minus A whole cube we need to find. If A and B are two matrices, then A minus B whole cube is equal to A cube minus B cube minus 3AB of A minus B. So that I minus A whole cube, we can write I power 3 minus A power 3 minus 3 into I into A of I minus A. Since I is an identity matrix, I power 3 will be equal to I minus, and here A power 3, here A power 3 we can write it as A into A square, which is equal to A into, since A is equal to A square, so we can write A square as A, and again A into A square, which is again considered to be A. So therefore A cube is equal to A minus 3 times I into A will become A, because identity matrix is multiplied with any non-zero matrix can be considered the same matrix A, of I minus A. So I minus A minus 3 times A into I is again A minus A into A is A square. So I minus A minus 3 into, we have that A minus A square is 0. So here we can say 0. We can write I minus A minus 0. So I minus A whole cube we can consider to be I minus A, which is our option 1. Option 1 is the answer. Given A and B are two matrices such that the product AB is an identity matrix and the order of the matrix B is given 3 by 4. And we know that the product of the matrices A and B is defined if number of columns in the first matrix should be equal to the number of rows in the second matrix. So these both must be same, and the product matrix AB will have the order of the matrix is M by P, means M rows and P columns. And here identity matrix must be a square matrix, so either it should be like a 3 by 3 matrix or by 4 by 4. and according to the condition, the order of the matrix is B is 3 by 4. So A matrix must have the columns as 3, and because it is a 4 columns are there, so it should have the 4 rows here to make it as a square matrix. So therefore we can say order of matrix A must be 4 by 3. So option 3. Which of the following statements is not correct? So first option. A row matrix has only one row. Yes, a row matrix will have only one row and any number of columns. So 1 by n is the order. So we can say one row, which is correct. And coming to the second option, a diagonal matrix has all its diagonal elements equal to 0, which is not correct. A diagonal matrix is Aij is equal to 0 for I is not equal to j. Means other than the diagonal elements, all the elements should be equal to 0. So here A11 0 0 0, A22 0, 0 0 and A33 for 3 by 3 matrix. Just consider where A11, A22 and A33 can be any other elements, any other elements. It need not to be zeros. So second option is not correct. And coming to the third option, symmetric matrix. Symmetric matrix is A transpose is equal to A, that is A dash is equal to A, which is correct. And skew symmetric matrix, A transpose is equal to negative A, or we can say Aij is equal to minus Aji. So which implies that whenever the diagonal elements are there, A11, or we can say Aij plus Aji should be equal to 0, and when the elements A11, when I is equal to j, so I can write Aii plus Aii, that is 2 times Aii should be equal to 0, means whenever I is equal to j, the element should be equal to 0, that is all the diagonal elements are equal to 0, so we can say this is correct. So among the 4 options, second option is not correct, so we can go with an answer 2. Given a matrix A is equal to 1 1 1 1, a 2 by 2 matrix, and satisfies A power 6 is equal to k times A transpose of the matrix A dash. So let us consider A square, which is A into A, 1 1 1 1 multiplied with 1 1 1 1. So multiplication of matrix row with column. So we can write 1 ones are 1 plus 1, that is 2. Similarly, the other elements are also same. So 2 2 2. And now A power 3 is equal to A square into A, that is 2 2 2 2 is multiplied with matrix A, that is 1 1 1 1. So we're getting here 2 ones are 2 plus 2, that is 4, and remaining elements are the same. So here we can add 2 square, 2 square, 2 square and 2 square. And so similarly, for A power 2 you are getting 2 power 1, for A power 3 you are getting 2 square, so A power 6 will get 2 to the power 5. So we can take 2 power 5 common, and hence we can add 1 1 1 1, and also given k into transpose of the matrix A, that is k into 1 1 1 1 transpose, which is equal to interchanging the rows and column, will give the same because all the elements are same here. And now when comparing, Ka transpose is equal to A power 6, and here 2 power 5 times of 1 1 1 1 is equal to K times of 1 1 1 1. So in comparing, you are getting K is equal to 2 power 5, which is 32. So we can give the answer 32, which is option 1. Given a matrix A is equal to K to 2K, and determinant of A power 3 is equal to 125, then what is the value of K? And we know the determinant of AB, we can write it as det A into det B. So similarly, determinant of A power 3, we can write determinant of A into A into A. We can write it as a det A into determinant of A into determinant of A, that is det A whole to the power of 3. So let's find the determinant of the matrix A. So here AD minus BC, that is K square minus 2 into 2, that is 4. K square minus 4 is the det A. And here if we can apply K square minus 4 whole to the power of 3, which is equal to 125. So K square minus 4 is equal to cube root of 125, that is 5. So K square is equal to 4 plus 5, 9. So K is equal to plus or minus 3. So the value of K can be taken as either plus 3 or minus 3, which is our option 2.